In the previous video, we explored about compiling a source file, and we generated the .o file for a source file. As I said, a .o file is called as a relocatable object file. In this video, we are going to explore what exactly is a relocatable object file, why it is called as relocatable. First of all, the main.o file, which is created in our case, is in the ELF format, that is executable and linkable format. ELF is nothing but a file format for object files and executable files when you use GCC. A file format standard describes a way of organizing various elements of a program. What are the various elements of a program? If you have a program, then your program contains data, it contains read-only data, what we call as constants, code, uninitialized data, and various other things. A standard is nothing but it describes a way of organizing these data and code in a file that is governed by the ELF standard. There are many other file formats. For example, COFF, that is the Common Object File Format, which is introduced by Unix System 5. If you are using ARM-CC compiler, then the compiler uses a file format standard which is introduced by ARM, that is ARM Image Format, AIF. And there is also one more file format called srecord, which is introduced by Motorola. There are various other file formats to represent object file and executable. But since we are using GNU-based compilers here, the compiler follows executable and linkable format. By using that executable and linkable format, you can create other formats, like you can create .bin or Intel hex and so many other things. So what main.o contains? Mainly machine-specific code and the data of the program. It doesn't contain any absolute addresses for data and code of the program. Let's explore main.o by running some object file analyzing tools. Let's get into the command prompt. Let's get into the workspace, and now let's run some command. In order to analyze the object file, you can use the command arm none eabi object dump. This command helps us to dump the contents of the object files. If you just run this command, it shows what are the options you have to use with this command. For example, let's just use let's say H, which displays different sections of the object file. I would use -h and the file name main.o. Here it is. As I said, this is in the ELF format. You can see that the file format is ELF32 and little endian, and this is for ARM. These are the various sections of this file. There is a .text section. This section holds the code or instructions of the program, and this section holds the data, especially it is initialized data, and this section holds all uninitialized data. This section holds the read-only data of the program, and these are some of the sections which are added by the compiler. For us, we should care about these sections because we have the control to influence these sections. These are some of the standard sections of the ELF standard. Apart from these sections, you can add your own user-defined sections, and that we'll see in the later lectures. Let's observe the text section. For that, you have to use some other options. Here I can use the option -d, that stands for display assembler contents of executable sections. What I would do is I would just use -d main.o, and I will redirect the output to some file. Let's say main_log. Here it is, main_log, and let me open this. Here it is. This command helps us to understand various assembly level instructions generated for different functions of our program. These are the assembly instructions generated for the main function. And this is for idle task function. This is for the task handler 1. And you can see that by using this command, we can disassemble the object file to observe various instructions generated for different functions of our program. All these are part of .text section. You can see that disassembly of .text section. What's the size? The total size of the text section is this much. If I convert that into hex, so it would be 4E8. The text section consumes a 1.2 kilobytes of code memory space. And you can see that the data section is only 1 byte. Let's run some more commands. Use the same command with different arguments. Let me use the option -s, full contents. Display the full contents of all sections requested. So here it is. This displays contents of different sections of the ELF file. These are the contents of .text section, which is nothing but collection of opcodes. These are the machine instructions or opcodes. Let's take a look into the contents of section .data. Here you can see that .data section consumes only one data. The size is just 1 byte. Later, I will explain how data is segregated between different sections like .data, .ro data, .bss, etc. There are different types of data like, as I mentioned earlier, constant data, initialized data, uninitialized data. So all those data go to different sections. I will explain that later. Take a look into RO data, that is read-only data. This section consumes all this data. These are constant data of a program. And these are some of the comments or some metadata added by the compiler. We did not worry about that. You can even run one more command, a -D, and then redirect this output to log. This command helps you to get the disassembly of all the sections. Usually we use the word disassembly to only text section, but this command helps you to observe various other sections. Let's say I have .text, search for .data here, which is right here. You can see that the .data section has this variable value, that is current task. This is a global variable, and that global variable is part of .data section. Why? We'll see that later, because I will explain different types of data in later videos. Here you can see that there is one more section called .bss, and this variable global tick count is part of .bss. Why global tick count variable is not part of .data and why it is part of .bss, that is the important thing what we need to understand, and we'll do that in the later lectures. Here it is. These are the contents of .ro data. These are the constant data. The compiler automatically translates these things as commands. When you are looking at data sections, don't give attention to these assembly instructions, because this is just a translation what the compiler did for these data. These are not true instructions. I mean, these data sections, that is .data, .bss, RO data, they have data. They don't have any instructions, remember. Why you see instruction here? Because we ran disassembly command. What that command tries to do is, it sees every number as an opcode and it tries to map that to an instruction. That's the reason why you are seeing here instruction. Basically, this section doesn't contain any instruction. All these sections, they contain data. After that, this comment section and attribute section, those are added by the compiler. Why it is called as relocatable object file? Let's take an example of our main function. These are the instructions generated for the main function, and these are the opcodes. This opcode is placed at this address with an offset of 0, and this opcode is placed at this address with an offset of 2. Like that, the offset is maintained. The next function is idle task, and this offset is continued here, treating this as the address of this function. This address is relocatable. This address is not an absolute address. You should mention the appropriate address here. And you do that by using the linker script. Because in our microcontroller, the code space starts from 0x08000000. The code space doesn't start from this address. That's the reason why it is called as relocatable sections. You have to relocate these sections or these opcodes to some other addresses as per your microcontroller address map. Let's say I compile one more file. Let me open the make file. Let me add one more target here. Let's say I call it as led.o, and I would call led.c. After that, I add one more target here, make all, colon. The dependencies are main.o and led.o. When I run make all, the make command will try to resolve the dependencies. The dependencies are main.o and ld.o. That's why it is going to compile all these subsequent targets, main.o and ld.o. Let's try this. Make all. Now you can see that I got ld.o. Let's disassemble ld.o. So ld log. Let me open this ld. Here you can see that this is a disassembly of ld.o. And here is the .text section of led.o. Here you can see that the base address is 0 again. In the case of main.o also, .text started at the address 0. That means the .text section of both the files are located at the address 0. That means there is a conflict. Then the opcode of both these files will go into the same address. That's not possible. That will create a conflict, isn't it? That's the reason you should relocate them. And we do that by using the linker script and by assigning the relocatable address to these sections. The relocatable address you have to decide based on your microcontroller or processor memory map. That we'll see later. In every object file, you can see that the base address is selected as 0. From there, the offset is counted. For example, if you go to the data section, it doesn't have any data. In the main, so if you go to the data section, you can see that again the base address of the data section is selected as 0. That's not true. You have to relocate this to some appropriate address. You can see that .bss also has the base address of 0. RO data also has 0. You have to assign correct or absolute address to these different sections of the .o file. Then only your program will run properly. In the next lecture, we'll discuss code and different data of the program, and I'll see you in the next lecture.